Hello, everyone. Welcome to ECE 335 Lab 2. In this lab, we're going to talk about PN junction diode, and we have a couple of experiments that we're going to run with these junction diodes. So the objective of this experiment on the lab is to learn about PN junction diode behavior in terms of their current and voltages that are when we operate in circuits, they have certain attributes that we want to figure out. And also, the another objective of this project is to characterize two types of junction diodes and find out their parameters that define their characteristics. So first, a little short introduction on how these junction diodes work in terms of as a semiconductor device in a circuit. So I'm gonna go over a little bit of background on how these diodes are created and how when we connect them in the circuit in a circuit with a supply voltage and other circuit components, how they actually behave in terms of current and voltages in the overall the circuit. So let's start with the diode physics a little bit. As we know that a PN junction diode has two regions, which is a silicon or any other semiconductor material that has been doped in P-type and N-type regions. And there is a boundary in between these two regions. As we know that the P-type material is basically any trivalent material that has been introduced in the silicon as an impurity, and those actually create a lot of hole carriers in this region because in their outer shell we have three electrons. Those make covalent bonds with silicon lattice, silicon molecules, but there is also another silicon atom that cannot find a fourth electron from these p-type material. So there is an empty shell in there. In the outer shell, there is an empty space for an electron, which we count as a hole carrier. And for the N-type material, those are pentavalent. So they have five electrons on their outer shell, uh, four of which makes four of which make covalent bonds with the silicon around them, and you have one extra electron that works as a carrier in this region. So you have hole carriers and electron carriers on these p-type and n-type material. So when we create these diodes, there is a zone in the middle, which we are going to call depletion region. How that region forms is that on the border of these p-type and n-type material, you can assume that there is a lot of electrons that are coming from the n-type side to the border, and there are a lot of holes that are coming from the p-type side to the border. So where we actually have the junction between this p-type and n-type material, the electrons will uh, quickly go over to the hole side and occupy that whole space because it's an empty space with a lower potential for them. And then once these electrons leave their native crystal lattice point and go over to the left, it basically creates a um, negative polarity or electron increase of electron over on this side. And since they left their native position, they create a positive charge over on this side. So you can assume that these charges that are created in this region are called space charges because those charges are not going to move. The charge element from them is just because of the recombination of these electron carrier from the right of the n-type material to the hole carrier on the left to the p-type material. So once you have these space charges, you can see that the positive charge will be on the right side here because the deficiency of electron, and the negative charge will be on the left side over here. So if you have a positive charge and a negative charge, it clearly creates an electric field, which points to the n-type direction in the positive and positive polarity, and the p-type side is the negative polarity. So when we connect this diode with a power source, a supply voltage, uh, typically if your voltage is zero or a very, very low value, less than submicron and other submicron, like millivolt or even lower than that, at that point, there will be no current flow because this electric field created in this depletion region will prevent any kind of electron from the N-type material to go over to the P-type side, and vice versa. They will also prevent, it will also prevent the P-type side holes to go over to the N-type material. Once you start to increase that voltage, at one point, we will cross over, we'll create enough electric field on the opposite direction when an electron from the N-type material will gather enough force to go over to the P-type material, and we will start to conduct current through the diode. At this point, we are calling that voltage as V on. So if we plot that current voltage plot in a curve like this, then you can see that at certain point, this current will start to increase. Up until that point, the current is very, very small, so you can barely see them above the zero axis line. But once you cross over that V on voltage, which is basically nullifying the effect of that electric field, then you'll see a sharp exponential rise of current in the diode. So the behavior of that current is explained with this equation, ID, which is equals to IS times exponential VD by NVT minus 1. I'm going to explain the parameters explained here, like variables mentioned here in a bit, but let me just go over this phenomena when we're applying a voltage across this diode in the positive direction. That means that the positive side of the supply voltage is connected to the anode or P side of the diode, and the negative side of the supply voltage is connected to the N side or the cathode. So this is the circuit symbol for a diode, and in reality, it's usually a cylindrical device. So on the device, to recognize the cathode and anode terminal, you have to look for a stripe. Usually, if your diode has a darker color like black or ash, then you will have a whiter or lighter stripe on one end, or you can have a diode which is golden or copper color. In that, with that diode, you will have a black line over here that denotes the cathode terminal for the diode. And then the other terminal is obviously the anode terminal. So when you connect this device with a power source and other component, if the anode is connected to the positive polarity terminal of the power source, then this is called a forward bias combination or forward bias connection, meaning that there will be the depletion region will decrease because of the extra added electric potential on this device, and then the electrons will start to flow after it crosses the voltage across it crosses this V on point. We are calling this an on voltage for the diode. So one of the tasks of this lab will be to find out this V on voltage of the diodes that we are examining. And then if we are flipping the polarity of our power source, or we are flipping the polarity of our diode and connect it in the reverse direction, that means that the positive terminal of the power source is connected to the cathode, and the negative terminal of the power source via other component is connected to the anode. Basically, we are putting a higher potential point at the cathode and a lower potential point at the anode. In that regard, we will say that the current is connected in a reverse bias condition. And when we apply enough voltage, we will start to see a reverse current flowing. As you can see in this plot, that this reverse current remains constant for a very small value, but that remains constant up to a certain voltage, applied voltage. And this reverse current constant value is called reverse saturation current. It is common in both forward and reverse bias condition. That's why you can see that denoted in here as a constant, which is IS. That is called the reverse saturation current. That is also a diode parameter or diode characteristic parameter that we are going to derive and deduce from the devices that we are examining. Usually for a diode, it shows how much your current will be in the reverse direction until it breaks down. So that is the third phenomena, which is the breakdown or breakdown region. That happens when we apply a large voltage across the diode in the reverse bias condition. What happens is we basically, when we are starting to apply a reverse bias voltage, the depletion region starts to increase on both P side and the N side of the material. That means that we will strengthen the electric field that has been generated in the beginning. And once we apply enough voltage across it, there will be a particular critical point. When we cross that voltage point, our electrons from the N side will uh, rapidly cross over that electric potential barrier and conduct through this device. And that is actually called a breakdown condition or breakdown region. And that voltage where the diode breaks down is called the breakdown voltage. That is also a characteristic of these diodes. And often for PN junction diode, this is a catastrophic failure. At this point, when we recover, the diode sometimes cannot operate in the same manner as before in the forward bias reaction. Or even if it works, it's not going to be it's not going to follow the same path as before in terms of IV characteristics. So it is often considered like a careful notation to our circuit operation so that our diodes are not in any kind of reverse bias condition and a huge voltage is applied across it so that it may break down. So that's a matter of caution that we have to consider oftentimes. So we are going to observe these phenomena, and then our goal is to find these parameters. So let's go back to this current equation, which is the diode current across the diode. Through the diode, what current is flowing in the circuit. As I said, the IS is the reverse saturation current. So the next parameter is the VD, which is the applied voltage across the diode. When what we are applying across the voltage. One point to consider, it is not the supply voltage when there are other components in your circuit. You may have a resistor, you may have other components in your circuit along with the diode. So always consider when we are using this equation, this VD actually means what is the voltage applied or a voltage across the anode and the cathode only, not the entire circuit or not the supply voltage. So you may have a completely different or higher value at your supply voltage and other points in the circuit, but the voltage across the anode and cathode of the diode is called VD. So the next parameter is the NVT that you can see here. So the VT is actually your thermal voltage. I have explained that here, which is VT is the thermal voltage, which is expressed with the equation KT over Q. This is a constant voltage when we are analyzing any kind of device, electronic device or electrical device. This is a common phenomena that happens because when a device is at a temperature, the lattice and the electrons inside it are going to have a vibration due to the temperature and the thermal energy. And that thermal energy will translate into a potential, and that is called the thermal voltage. And the way it expresses it is a KT over Q, where K is the Boltzmann's constant, and then the T is the temperature of the device in Kelvin scale, and Q is the electron, excuse me, is the charge of the electron. So as you know, like these constant values are well known. So you can just look up the values of KT, K or Boltzmann constant, and Q is, I think, it's all known to you as 1.6 into 10 to the power minus 19 Coulomb. And T is generally your room temperature where we are running this experiment, and that is 300 Kelvin. And if you make a simplified equation calculation here, then VT is usually around 26 millivolt or 0.026 volt um, in room temperature condition. So you can use that in your hand calculation as a starting point. And then the last one is the N, which is a non-ideality factor. It is a constant for every diode. Ideally, the value is supposed to be 1 when we are applying it in a model or in a hand calculation mode. But usually, in reality, you can find the value in between 1 and 2. So our job here is to find out all these constants for the diode characteristic constants of these values are of IS and values of N with respect to finding out this plot. So if I plot the ID versus VD plot here in figure 1, then from that plot, we can derive these constants for that diode. So the diodes that we are going to examine, one is the regular PN junction diode, and that part number is 1N4004. The library file and the parts are available in the part store, and the library file is provided with the assignment at the assignment page of Lab 2 on Canvas. And the other diode is 1N5231B, which is a specific kind of diode. I'm going to talk about that right now, which is a Zener diode. So what is a Zener diode? A Zener diode is basically a type of PN junction diode, which has a heavily doped P-type and N-type region. By doping it heavily, what we create is a diode which has a very narrow depletion region in zero bias condition when no voltage is applied across it. You can see a qualitative figure here where you can see the PN junction diode with a depletion region in between here, and then a narrow depletion region in a Zener diode. What happens is this Zener diode specialty is that we usually use it as in the reverse bias condition. So it usually have typically it has a lower breakdown voltage than the regular PN junction diodes breakdown voltage. And when it breaks down, we usually get a very linear, sharp rise of the current. You can see over here in the pink plot here. So we are applying a negative voltage. And at this point where it says VZ, we are going to break down this Zener diode. And that current, the current that we are getting here, the IS value is going to increase very sharply and in a linear fashion, almost like there is a resistor in the position of the diode, where you are going to get a resistive effect across the diode. And then you can measure the slope of the diode, which is the conductivity. And then if you reverse that slope, you get a resistor value for the model of the diode. So, and you can see that the voltage across the diode, after it breaks down, it's not going to increase very much. So it's sort of like works like a voltage regulator or voltage source, where you have an almost constant or very insignificant fluctuation of voltage across the device, while you have a high change of current depending on the other parameters in your circuit. So we can treat the Zener diode as a voltage regulator. That is one of the most common application of this diode and why that is used in regular circuits. And you can see the circuit symbol of Zener diode is a little bit different than the regular diode symbol, where this is the line that defines the cathode, But for Zener diode, you can see the ends of the line is a little bit bent in this manner to signify its breakdown behavior over here. So the other device is labeled as 1N5231B. So it will have a different type of characteristics when it breaks down. So we are going to experiment with this diode in the breakdown or reverse bias condition, where we need to find the values of RZ and BZ, the breakdown voltage and the Zener resistance of this diode. So let's go back to the PN junction of experiment one. So the experiment one is about the PN junction diode. So what we have to do, we will start with the hand calculation of this equation. So you can assume you can solve this ID current equation for the diode with respect to the applied voltage across it. For this experiment, we are going to apply a VD voltage from 0 to 1.2 volt across the diode, while we want to observe how much current is going to draw. And then we are going to define and calculate the values of IS and N in this equation. And VT is already known, which is KT over Q. So the way we find the IS and N is we can simulate, you can calculate up to that boundary condition of VD. Say we are applying a voltage of VD at 1.2 volt, and we are going to observe the current which is there in this circuit that is shown in figure 3. So let's assume this R1 value, we can choose any value of R1. We can choose 100 ohm, you can choose 1 kilo ohm. And then if you have a voltage source which is a slightly over the 1.2 value, to get the 1.2 voltage drop across the diode, then you can get the overall current from assuming that you have a resistive VR voltage drop across the resistor, and you can do that calculation pretty easily since it's just two component circuit. These are mostly given as a design scenario to you so that you can derive these values with an expectation of how they're going to be. And then when you go to simulation, you can set up your circuit with those values and start your simulation. You may have to tweak the values later on with looking at the overall current plot, but that is how you should start with the hand calculation first, applying the values from your text. So in LT-SPICE, what happens is when you place a diode, it usually creates a generic diode with a generic model. But since we are using a specific diode device, the 1N4004 and 1N5231B, so we are going to use their specific library files. The library files are text files that define the diode as a model. It usually has a model or a subcircuit. For this case, the PN junction regular diode has a model, which is this file. But the Zener diode is explained as a subcircuit. Basically, for the simulator, the simulator is going to look at the Zener diode symbol, and it is going to replace that symbol with a circuit which has a voltage source and a resistor, like we just discussed about Zener diode behavior. So that subcircuit definition and specification is given in that .lib file. So you can open it in any kind of text editor and look through and read through that file. It usually has a command which is .model, and then the name of the model, and then the definition and all the parameters of that model. Or it can have a subcircuit for the Zener diode's case, and then you'll have a subcircuit name, and then you'll have the definition, the netlist of the subcircuit and other definition of that diode in that subcircuit. So the way you define it and assign it in your LT-SPICE simulation is that when you draw this circuit, you place a diode, or Zener in your circuit, and you connect the wire of the entire circuit. Then, excuse me, what you do is you press Control and right click on the diode and open up this component attribute editor window. And on this window, you can see that the prefix is D, which means it's a diode, and value by default is D. But we have to change this value with the model name that we have in our library file. So open up your library file and find out this dot model command. And whatever name is given after that, uh, you copy that and place it in this value field. And then save this attribute editor so that that will be assigned in your diode. Once you save it, the symbol here, like this D text here, will be changed to the model name that you have. And then you need to add this library file location as a SPICE directive in your circuit. The way you do it is you open up a SPICE directive or add a SPICE directive. You can hit T, the letter T on your keyboard, and open up the SPICE directive window and write .lib. And the part.lib is basically a generic name, but replace the part section with the model name or the file name that you actually have in your directory. And the files provided in your canvas, just download that and place it in your LTSpice home directory where you're running your LTSpice simulation from. And then copy the name of the file with its extension. It's usually .lib. So just copy that and place it in your SPICE directive for the LTSpice circuit. And then place that command in your circuit here, and then place it in anywhere in the window, and it will be added there, which basically tells LTSpice that you should add this library and look for this file in the home directory or the LTSpice home directory, and use the model definition inside that library file to run your simulation. And you have to do the same thing for the Zener diode simulation also. Just add that library file with the .lib command in your LTSpice circuit. And then add your voltage source and ground as required, and then run the simulation. When you run the simulation, you are running a DC sweep on the source voltage here. But when you are plotting the ID current through the diode with respect to the VD, which is the voltage across the diode. And the way to do it is you can name these nodes, and you can edit that in your plot window, where usually when you sweep a voltage like V1, you usually get the current versus the V1 or the source voltage. But if you double click on the axis value, then you can edit the voltage parameter. You can put VN1 minus VN2, which basically means you are subtracting the node voltage 2 from node voltage 1, which gives you the voltage across the diode. Then your plot will modify according to that. Your current will give you the accurate ID versus VD plot. And it should look ideal, look close to the ideal value. But make sure with the notation that your voltage on the x-axis is not the source voltage, but the voltage potential between the nodes across the diode. And once you do that, you may have to change the values a little bit on the source or the resistor side. Make sure to choose a resistor value that is reasonable. That is not something that you cannot actually build your circuit with. Then you should be okay. And also for the maximum current, you want to limit the total current that flows through the diode in your experiment setup. So in your simulation, you may generate as much current as you want. The model will not hit that point since it's a large current that can flow. Usually your simulation will show you some result, but when you actually build the circuit, you cannot actually flow maybe that current because the diode cannot handle that much high current. To make sure that your diode is safe and your circuit is safe, look through the datasheet, the device datasheet that you can get online. You just have to search with the diode name, which is in this case 1N4004. So if you just search 1N004 datasheet, then you can get the datasheet for this diode, where it usually mentions it has that value for forward bias current. You can see the maximum current that you can flow through these diodes. And when you are actually designing the simulation test bench, make sure that the maximum current through this diode is not reaching more than 50% of that rated current in your datasheet. So, for example, if the datasheet says that the maximum forward bias current is 1 ampere, make sure that in your simulation and in your circuit, it never reaches more than 0.5 ampere or 500 milliampere. And that's why you need to change the resistor value or change the source voltage value, so that your voltage and current across voltage across the diode and current through the diode remain in the rated region, like a safe region. So that's pretty much how you run the simulation. You would have to repeat the same thing for the Zener diode, but in the reverse bias condition. Once you run the simulation and you get the ID versus VD plot, then you can actually find out the values of IS and N from your simulated circuit. The way to do it is explained here. So you can take a log, natural log of your current. So to do that, you have to hit the current axis parameter and change it to ln IX. So when you do that, if you put the ln across the ID or IX current, then your plot will be in the y-axis, it will be in semi-log scale, and in the x-axis, it will be in linear scale. So it's a semi-log plot. So when you turn it into that, you can see that the y-intercept gives you the ln of IS value. So in your plot, you will see where it cuts the y-axis. That value is your ln IS. And the slope of the straight line that you get is 1 over n VT, where you know the value of VT, so you can find out the value of n for your diode. And then you can actually determine from the linear plot the on voltage for these diodes. And this analysis is similar for both the regular diode and the Zener diode. The only other specific parameter that we will need to find for the Zener diode are the VZ and RZ value. And the way to do it is, once you plot it in the reverse bias condition, make sure to mark the point where it crosses from where it actually starts to break down and increase the like the current is going to increase at that point. So that point is your VZ or Zener voltage, and the slope of the current plot is going to give you the RZ 1 by RZ value, and you can find out the RZ value from that. So you can plot them in MATLAB and get the data extracted from LT-Spice and plot them in MATLAB. And then you can generate or calculate these values from simulation. So once you're done with the simulation, you basically go into your experiment. You build your circuit on a breadboard and connect it to the power source and apply the same voltages that you have applied in the simulation. For the simulation, what you did was for the regular diode, you applied a positive voltage of 0 to 1.2 with a step size of 0.1 volt. So increase your voltage from 0 volt to 1.2 volt with a step size of 0.1 volt and record the current that is flowing through the diode. You can add an emitter over here to measure the current in the loop, or you can measure the voltage across the resistor and divide the voltage with the resistor value and get the current value directly from there. So there are like two ways you can actually measure the current for respective voltages that you are, like the step voltages that you are getting from the supply. So that plot is, you are going to superimpose that plot or plot it in the same axis with the simulated plot. So we can see whether the experimental data matches the simulation data. And for the reverse bias, also you have to apply a voltage in the reverse direction from 0 to 6 volt and see where and measure the current at each point to see where it actually, the Zener diode actually breaks down. So that's your lab experiment too. And also in that circuit also use a resistor to limit your current. You can do that calculation you can also see it in a simulation how much current your Zener diode can tolerate in the reverse bias condition, and then make sure to apply 50% or less than 50% of that current. And for the report, you have to include for both diodes, for both experiments, you have to add the simulated plot, IV plot, with the experimental IV plot in the linear graph, so that we can see whether they deviate or whether they match in terms of their trend and in terms of their values. You may have to explain why if they have too large of a deviation, then you may have to explain why that is. Maybe your resistance values do not match properly. Maybe your supply voltages or the steps that you have taken did not match properly, or your model parameters may be very different than what you have actually gotten from the simulated data. So all these are possibilities of having a large error between simulated or experimental data, but those should be well explained and well documented in your report to make sure that you understand, you understood the circuit and its experiment well enough. So explain it in that order. And also, what you have to do is you have to create the logarithmic current versus voltage plot for these two devices in forward bias condition to find out their IS and N values. You have to do this for both of the devices and only the reverse direction for the Zener diode to find out the VZ and RZ values. So include those plots and their explanation, like a short explanation with them. And also the schematics should be readable and properly labeled on the axis, and all the legends should be properly labeled, like which is your experimental data, which is your simulated data, etc. And it should have your hand calculation, like how you estimated the maximum current and maximum voltage for your circuit, and you should include the simulated plots and the experimental data plots, where you have the data points listed in a table, and then you include the tables for both diode and the parameter comparison. So the parameters that we are comparing, you are actually using a resistor in the circuit, that's your R1, and you are comparing, you're finding out the V on, IS, and N parameters. And these values, you are finding it from a hand calculation, you're finding it from your simulation, and you're finding it from your experiment. So chart all of these parameters in a table and show us how much they deviate from each other, like the percentage of deviation from the simulated data or the hand calculation data to the experimental data. That actually gives you a full view of the whole experiment or the whole characterization of the diode. And then for the Zener diode also, you have a resistor in the circuit R1, and then you are measuring the VZ and RZ values. You are also finding out the V on and IS values and N values for the Zener diode in the forward bias condition, but that is not we are going to check for that one. It is similar to the PN junction diode, so you may not have to mention it here. But the more important parameters are the Zener voltage, breakdown voltage, and Zener resistance. So those you have to do the hand calculation and the simulation and the experiment deduction for those three, and then compare them in a similar manner in the table. So you have a checkoff sheet here. So once you build your circuit and run your experiment, and you gathered all the data points, you should sign off, get a signed it off from TA, like contact me or send me an email once you are done. You have to demo your circuit, and you have to, all your lab members, like all your group members have to be there to show your circuit, because all of you are required to work on your circuit and present it in a way that you actually understand what you have experimented. And usually, when you are showing it this data, we will give you a signature if your data is correct. But we will definitely ask you about the circuit and the experiment, how you have derived these values, or how you have done the experiment, which steps did you take to, like, a certain caution or certain expectation, like have you measured this value using an ammeter, or what values did you measure, or did you use a voltmeter or a multimeter to measure the voltage across the resistor, etc. So unless you do the experiment yourself actively, you will not be able to answer those questions. Then it will reflect poorly on your overall lab performance. So I would suggest everyone to run the simulation and the hand calculation yourselves. You can do it as a group, but understand what steps you are doing and what calculation you are doing. Um, it's usually best to do it yourself, so that once you get stuck or you hit some problem or issues, then you actually learn from that, how to solve that issue, and how actually going to get the correct simulation or correct calculation. And then definitely run the experiment yourself, if not all, but measure part of the data when you are very sweeping the voltage supply for these diodes. One of you can measure it on the forward bias direction, one of you can do it for the Zener diode forward bias direction, and one of you can do it for the Zener breakdown, like reverse bias condition. So etc. Like you can divide and you get an experience of measurement and actual running the experiment, and that is very valuable experience that will give you a better understanding of these diodes characteristics and how they behave in a circuit uh, situation, like circuit environment. So that's pretty much everything regarding this experiment, regarding this lab project. So the way it will be graded is that on your hand calculation of your voltages and currents of the circuit, that carries 10 points. Then your simulation and experimental results, your plots and calculation and the derivation of the values, they carry 15 each. And then the TA sign off, which is after the experiment, that carries 10 points on its own. So in total, it's 50-point lab. So make sure to perform all the sections correctly, so that you will get the full points on that. So good luck with the experiment, and make sure, please reach out to me if you have any issues with the simulation or the circuit building or the data collection. At any point on the lab, please send us an email and contact us. Don't waste any time just handling the issue and not solving it in time. And your due date will be September 30, which is listed over here, which is a Monday, like from next Monday. That is your from next week's Monday. So just make sure to go over these details. There is also a text file uploaded on the assignment page. Go through the diode background, like how they derive these equations and how they actually solve some of the examples, specifically example 3.3 and 3.4 on page 81. That actually shows you how you can do your hand calculation. I think it's example 3.3. So go over that. And if you still have any question about the concept, any kind of confusion about the concept, just reach out to me. I will be more than happy to help you with that. So good luck, and we'll see you guys in the next class. Thank you.